Hello, and welcome back to Old School Coding, where I'm using the C programming language C99 to construct a simulation of an 8080 based microcomputer using the techniques that I used to use back in the late 80s and early 90s for producing software at the time. We are getting very close to finishing up the instruction set of the Intel 8080, which is one of the components of this simulation. And what we have on the screen in front of us is the T-state diagram table for the instruction set. This is actually the second page of it. And the remaining instructions we have are the RST instruction here, which is a 1-byte call to one of 8 locations in low memory. And we also need to implement the XTHL instruction, which exchanges the contents of the HL register with the word on the top of the stack. And we will get to what's going on in detail as we go. So between sessions, I worked out how I wanted to deal with the shadow. That is, when you boot the 8080, it needs to have ROM mapped at 0 so that you can have something executing that defines. I mean, unless you're on an MSI and turning on the machine involves toggling a lot of switches on the front panel to load in the boot sector and all that. But we want a ROM there, but we need the ROM to go away. So first, before I get into the instruction, let's get rid of the PDF here. And let's take a look at what I did in the decoder. I tried to bury the manipulations of shadow mostly in the decoder. There will be some interactions with the reset system. So let's bring up source i8080.c. Is it shadow? No, it's not shadow. That's right. So the link between resetting the system and resetting the shadow is actually in the test. So we consider the shadow mechanism to be kind of an external chunk of circuitry that will be provided by a simulation as appropriate to it. So there will be different ways of turning shadowing on and off, depending on whether you're simulating an MSI 8080 or an Altair 8800 or a Sol 20 or whatever you want. But the core of it is here in the decoder. I tried to simplify things a bit. So initially, when we first created decoder, it will have no shadow. And the way we're going to implement this is that the shadow pointer here will point to an edge that will be used to service all memory reads. That hasn't changed. So when we do a memory read, we need to honor the shadow. So during memr rise, I didn't finish implementing this. So memr is going to go low to become active and go high to release. And what I implemented earlier, without thinking too closely about it, was the first time I worked with shadow, I said, well, let's pick up the proper decode and the shadow. And if shadow is set, then we're either going to use it or turn it off. So if shadow is set, and we are actually accessing the thing behind the shadow. So the first time we access the ROM that got mapped down to 0. So when we jump up to where it is, the idea is I want to be able to execute a jump instruction at 0 during reset and have it land in the ROM and have shadow turned off. So here's how we do it. We pick up the proper decode for the address and the shadow. And if we have a shadow, then if the shadow is equal to the if they're the same edge, then we're going to turn off shadowing. We're done. And now I need to do the same thing for fall, except it's going to be edge low instead of edge high. And it's only memread that's going to do this. Memwrite, we do not do any shadowing, and IO, we do not do any shadowing. So there we have it.
Some days we got 4.
So
I'm a riding up.
with that in mind, the program to test the RST instructions becomes fairly simple. Our ROM normally lives in the top 2 kilobytes of RAM, of the address space. So we're taking the ROM from the top 2K and we're mapping it into the bottom. And the way I've actually done this in the implementation is the test system that's getting built has a number of ROMs and they start from the top. So ROM 0 is in the top 2K and ROM 1 is below that and so on. So this first ROM, which is going to be the one that will service shadow requests, maps at F8. So it'll start off with a jump up to itself. So boom, the moment we land here, the moment we do this instruction fetch of this first instruction in the ROM, shadow is going to turn off and we'll have access to RAM. So now we want to place a bunch of things here in our reset vectors, and we're going to do a whole bunch of RST instructions. So RST0 will do a call to 0000 hex.
If anybody has,
And what we did here was we wrote,
to do the little obsidian
let me break this apart here. Into each one of these locations that we call 0, 8, 10, 18, 20, 28, 30, and 38. These are the locations where the RST instructions land. We're putting a call in. So when the RST happens, it's going to push its return address on the stack, and it's going to land in these locations. These locations have calls in them, so they're going to push their address onto the stack. And then they're going to call this check routine. So this is CD is the call instruction, and HL gets the address. We're just going to store these. So this will establish our vectors. We set our stack pointer to point at a stack top and HL to point at where we're going to log some data, and that's both at 80 hex. So the stack will go from 80 hex downward, and then we're going to log some stuff at 80 hex going upwards. Now what we're doing here is each one of these guys is going to call check. It's going to pop an address into DE, which will be 43, 411, 4B, and so on. And I'm going to just take the low byte of that and I'm going to toss it into the log area, increment HL, and return. Really super simple test program. And now we need to implement the restart instructions so that we actually can run this. So source. RST will need to be pushing some stuff on the stack. It looks a lot like call. So let's take a look at call here. In fact, I think what I'm going to do is I will put the restart instruction in the call area. This means potentially that the address, we may in fact use the call M5, call M4 and call M5 to service this. Can we do that? Let's go back and look at the PDF again. So here's the call instruction. Normally it does some pre-adjustment of the stack pointer and fetches the address into WZ, and then it does the pushes, and at the end it's going to latch WZ into PC. So that's that normal dodge I've been using, which puts WZ into PC at the last moment here rather than deferring it to the M1 cycle. Now if we look at RST, RST also does a pre-adjustment of stack pointer in M1T4. It skips these two and it goes right into what appears to be the same. I'm going to use my finger as an assist here. So call SP out status, PC high, read from PC high, SP plus 1 onto data bus, SP out status, PC low onto data bus, and the difference here is that the temp register, which has our original opcode, is being put into Z. So very similar. What I can do is I can actually load up W and Z during the T4 service for RST. So once I get that, then I can just say, well, we're going to use the last, we're using M4 and M5 from call to finish off the push and transfer to WZ. And that's going to be real simple. So let's move the PDF out of the way again. Bink. Come on. So RST will have an M1T4. I'm actually going to put it up near the top. Does it have an M1T5? I forgot to look. Yeah, of course it does, because nominally what it does is during T4, it reads stack pointer into IDAL, and in T5, it's writing it back. And we're going to mess with W and Z in the background. The real CPU will be loading up W during T3. It'll be loading up Z during some other cycle. We can kind of wave our hands over that. So RST is just going to be there for int n equals 0, n less than 8, plus n. And you know what I'm going to do here? I will actually just write these as a sequence of instructions like that. So while we know the target address is in certain bits as engineers, this code will simply write it to the proper places. Now, RST M1T4, that's going to have to know what's going on. So call M1T4. Finish decode. This is call, becomes RST. So RST M1T4. Same thing here. We're doing the same thing with stack pointer. The additional thing we are also doing is we are putting something into W. We're putting a 0 into W. So dset W0. And I'm going to deset Z to a val of IR amper 0x38. So we're pulling out the operand bits from the instruction decode and using those to construct the destination address in Z.
Road book, the backstab, either of our roads need backstab.
Okay. Now M1T4 of conditions, we do not have RST conditional. We do need T5. In fact, I'm going to move M1T5 for call up above the conditional call stuff, just because I want to keep this a little better organized. So we have RST, T4, and T5. We'll have call, T4, and T5. Then we have call conditional T4, which will, I believe, dumps into call M1T5. Yes, it does. It decides call or not call. The real 8080 hardware clears W in M1T3. Now, is that actually correct, what I just wrote? Checking RST? Yes, that is true. So having done that, our RST instructions should now work. I am going to test RST separately from call. Remember, our call as LST call test.lst, we had this big thing for call and that we needed to test call without being able to release shadow. So it's not until the last bits of the testing of the CPU where we're going to say, well, we're going to release shadow and try other things. Now, could go back and rework this. Not sure whether we need to or not. It may or may not be helpful, but it's working as it is. So we're not compiling yet. So RST M1T5 was not declared because I didn't edit that properly. Okay, so now this is saying we have a test condition failure in reset post. I have changed something somewhere which is causing this test to fail. So, nothing I did should have made any difference to this. So we made changes to ASM test, RST test. We created that RST, well, we edited RST test. We edited call and we edited decoder. We edited decoder. So remember I changed memar fall to modify shadow. I don't want to release shadow yet. Is that true? So let's see, git checkout. Seems to me that if this version, if the old version of decoder that I've just reverted to, if this works, yeah, it works. So there's something weird about turning off shadow on the falling edge of memar. It is possible that what's happening is that memar is being activated before the address is being set up. Let's actually do something in there. Stub, releasing shadow. And I am going to continue using exactly this. Oh, I see what it was. No, it's not. I don't see what it was. I thought I was mixing up R and W for some reason. There's the difference. Memar fall was forcing a falling edge. Boom, there we go. That should be working now. Let's change this to a guard There we go. So yeah, if we erroneously thought that memr falling was just like memr rising, just with a change of the edge, then we have problems with reset. So there are assumptions in the code. That's fine. I even had a comment in there, force a falling edge needed during wait states. So probably what was happening was we were not coming out of our wait state at all. There we go. And of course, none of that printed because the code that exists right now does not actually exercise releasing from shadow ever. So it was never getting into these two lines. We're about to do that for the first time. We do compile. So call test.
Yeah, y'all are going the wrong way.
We do have a call test source file here. So call test needs to do two things. In fact, it's different enough. I will create a i8080 RST test.c. Test the RST instructions. Okay, everything is good. Now we just have to modify here to test the appropriate results for the RST test. So it will be modifying the stack below the stack top. There should be 4 words. So the test uses a stack growing down from 0. It should not use, only use 2 words. The test writes a trace log at 0080h forward with 1 byte per tested RST instruction. Two words. I am not going to have anywhere but that one location, knowing that the log starts at the same place the stack does.
East of the rock.
So let's see. For the indexes up to and not including stack min,
Yeah, watch
we
your
are
hammer.
unmodified. We wrote 8 bytes, so then we can go from log end to RAM test area size. So, and the value we expect to find here is going to be I minus log at times 8 plus the bias, which is going to be 3 bytes in. So this will go up by 3, and it will start out as RST0's address plus 3, because we've got that call that's going to push the return address. Boop. I'm going to print end here and print top here to make sure we're getting to it. And let's add it in here as well. So we should see a whole bunch of prints coming out once we get this hooked up. And this is also going to dump some plots for us. Let's see. Warning, unvalued variable exp. Well, that's bogus because we use it right there. Just call it. It is possible the exp is being confusing. Unused ROM. That's correct. We are not reading the ROM there, and we need to define that. So inc i8080 test.h.
The gloves or dark wisdom are reserved by Holy Death. Congrats, Holy Death.
There we go. So this says that we are getting into the test and that PC F840,
We have no reserves.
we are fetching the instruction C7.
So roll away.
So this is not good.
Very nice pinky cloak. Go into cool core in 3, 2, 1.
So
We have the head of the
F840
gives you a really nice neck piece.
is right here.
Go
This
into
says that I did not actually write to this location.
2. Ooh, well, that's close, but not quite.
So
Still tuned.
C7 was not hooked up to be RST0. That's not good.
Congrats to him.
Okay, there it is, RST0.
And we have a hilt token for priests, mage, warlocks, and druids.
And one T4 is being decoded right there.
We also have a shaman book. Nobody wants the token, I'll leave it on the bottom. And the book goes to Aya.
So here we're connecting C7 to RST. We're getting here into the post. And here we're saying this is unimp. So who is messing with op RST0 after this? So declared it, reset, fetch, yada, 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 yada. Initialize, 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 initialize. And that's it.
the performance.
We're getting there. We're getting there. We're getting there. We're getting there. And we're getting there. So somebody is messing with the decode for C7. Hold on. Yeah. So the compiler is going to complain about what I'm about to do because it's not really portable to cast a function pointer into a void star. So here, this says it's correct. Are we ever getting there? We are getting there this many times. And actually, I don't want to print adder. I want to print ID. I want to print the PC, which will probably be already incremented by the time we get here. So this is interesting. Oh, right. We're not completely hooked up yet. These things we do for call, we also need to do for all of these RSTs. So let's break the for loop. We forgot to set M2T3 and M3T3. Silly me. And we're still going to use the call. So this is looping forever. Okay, so what happened here? So piping it through head minus 1,000, it will say stop when we get to 1,000. That's still running forever. And it's not producing any output, of course. Okay. So what are we doing here? We set up all this stuff, then we do each subset, and we're supposedly bumping down into a dB10H.
I didn't see any
So
rules
let
on
me
the
actually
letter-working pattern.
put something back in and print. So in M1, see RST M1T5, I'm going to, no, let's do it here. So what we're seeing here is not the pattern that I wanted. And what I do want to do now is put in something where I can get a plot out at the other end. So we're going to RST. Come on. Going into here. And what I'm going to do is I'm going to put a test complete here. Yeah.
Oh, I'm being sacrificed. Oh, it hurts. It hurts. It hurts so bad. I've been paralyzed.
So our instructions that we're going to do there is a test complete, followed by the calls. So we should stop the first time we do an RST. In fact, what I am going to do now is before I do the first one, I will also do a test complete. I will start removing these as we get things properly set up. Now, our test should have failed because I wrote some stuff to low RAM. Okay? So when we got to the comparison, it should have failed. We never got there. Okay, so we have now terminated our test, and we got through it.
Luxury, do not leave.
And in our comparison, we said that
Cindy's not
we
here,
were
but that's
expecting
on you.
a
And congrats, I know you.
5A, we got a 1.0. So this is comparing RAM at 0. So now I-8080 RST test.
We have another warrior book.
And what I'm going to do is I'm going to do a print of the RAM so we can see what it looks like. Now I have some code in source ROM.
And hilt, warrior, hunter, rogue, shaman. Slacker.
That does a ROM dump.
To the slacker.
And I'm going to just grab that and put it right in here
And
because
Cindy's
I am a
not
total
there,
slacker.
Who's already part of CG. Save my spot.
So here's what we wrote. So 5A was the pattern from before, so we have 1.0, CD, and so on. So we know that we got to the first one.
Wasn't there somebody that said they would drop, but they wanted to?
Or did we? So we're not actually dumping any of the PNG stuff here. We should have dumped some diagrams. We are failing in post, so we're not doing that yet. So what I want to do now is disable it during post, just run it during BIST. So BIST prints out a whole bunch of things. We'll just
It's the same person.
I guess I got to do this. So the pattern is correct. We've got a 1.0 followed by the call instruction. So now the question in my mind is, why did we not see Oh, right, because I need to do that. So here it is, BIST RST. We have several of them. Let's get rid of them. Let's get rid of RST timing data. And we run it again. So RST1, this is going to be the first bit of our code running. So we cannot actually read the data here. But this should be a jump into ROM. And all of those STAs. And dbin is ending up high here for some reason. So somebody is not setting dbin to low. There we have it. So the first bit of the code is our jump up to the ROM. Why is the address bus not showing here? Ah, good grief. There's a whole bunch of things we should be tracing here that are not showing. Okay, second plot should be the move immediate into the accumulator. None of the whole bunches of the internal stuff are just not being dumped here. So we have a broken test infrastructure. Now that might be because we are aborting before we're properly releasing everything. In fact, that's probably true. Let's start off with that assumption. I am going to remove the abort in the test failure. The other thing I'm going to do is go back to this guy, and we are not going to do this. The test writes data to the area executed to low RAM that will be executed by the RST instructions. Okay, we're failing here now because we're not actually doing the test. We're stopping early. So we have failures on all of those, but we are going to get nice plots. And now that we are not exiting abnormally, we see the whole thing. So that there's that problem. If we abort the test program, the log data is not actually written out properly. Known problem. Okay, so here we go.
Water from luxury before they leave.
Ba-da-bum. We have PC 0, 1, 2, 3, F803, 4, and so on. Okay, and we have here, we have stores, so we can now go back to our test program. So I am fairly sure that we are doing the right thing up through the first RST. So what I'm going to do is I'm going to put in a subtest marker here. And test completion there. And we're going to stick a no op at the start of the first one. Actually, let's make that a separate thing.
So the way we do this is I pass out these we go along. If I get out of range, I do ask that you pass on coins and bijoux. If you happen to pick up a bijou, if you will just whisper me, I will write your name down because that's what I do when I pass them out. I like to try to make sure everybody gets a bijou. Also, I have a site that will be picking flowers. I like to send those to the Guild Bank to help with some, raid costs for people. But if a blood scythe is in one of the voodoo piles, then your herbalist will roll that off. But don't pick flowers, please.
So that should do our first RST, and we should come back. Log, timing, star RST star, make.
You gotta go up one notch on the,
Remove the images, then
whatever the green is. Yeah, I don't want to.
live coding BIST. I think it's make PNGs. Plots. And that is running forever.
Oh, I need assist so I can do raid running. And who can be my DEO? Clock?
Lardy, 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 lardy.
I see 87 Plume Walker. Congrats. Bag. Plume won it. Congrats.
So, apparently, my addresses are getting all screwed up.
Yeah, if we can clear this whole room because since they did the
Well, see, that explains why we have all of these FFs, because we're reading from basically garbage addresses here. So the first reset is F85C hex. Verify that. That should be correct. That is correct. Okay, so the address is beyond the DB. That's correct. I'm going to go ahead and decrement that by 1 so we get the address of the RST. And this says IR is C7, WZ is 0, and somehow we're getting to this address right here. So, I need to see an address trace of what's going on at that point, and we're not seeing it here. Yet. Because we're only getting this one plot now. This is the plot that's being dumped, which ends shortly after we set SP to 80. So this is the plot that's dumped here. And we execute the RST 0 and we go off into the weeds somewhere. So let's instrument our instruction fetches a bit. So when we get the IR in here, there we go. So we're going to have a whole bunch of this crap. And we finally get there. And RST test is there. And then we're getting to BIST. Post top, post end. Yeah, that's not long enough. There we go. There we go. So this is what's happening. 2000 was just barely long enough. So we did see our stuff at F8. We're crawling up through the code here. We've got a bunch of 3.2s. These 2.2s are the SHLDs. Here. Then we've got a 3.1 and a 2.1. And then we execute the 1.8. And here's the C7 for the RST. We get into the RST. We are getting to 0. So WZ is zeros. And we are getting there. And this fetch is saying, oh, we're going to this completely different address. So apparently I am not doing the right thing with PC. So what did I mess up? So M1T5 is, oh, it's right. I forgot to link it up properly. So what I ended up doing was replacing the M1, T4, T5 of call with the reset stuff, which set WZ. But then I went in and went back to executing the 2-bops stuff, which picked up 2 of the opcodes. I should have realized when I needed these 2 that there was something wrong, because we shouldn't need those at all. We should not be using 2-bops for the RST because we don't have a 2-bops. What we should be using there is CPU arrow state next is equal to I8080 state call M4T1. We want to immediately go down to the push. So, yeah, the hardest bugs are the ones that are the simplest solution, but the hardest to discover. So here is our new dump, and we're seeing that we're getting into the RST instruction here, and we fetch it 0, and we fetch it 1, and then we get to F8 6C. That's our check routine. So we're getting to check, and it's doing its stuff, and it's returning. The C9 is returned, and we're getting back to F8-5C, which is here. Yay! Which means I should be able to go back here. Do that, kill the test completes, and let her run.
Actually, I'm seeing caffeine with the Jindos. Back away. Congrats.
And right, we didn't have the live code. We didn't have the loop going because things were running infinitely. There we go.
And we have Coumadin, Shab, Inspo, and Stubbed on this idle. Those 4 people roll for me, please. Inspo and Stubbed.
Okay, so prep. We have our instructions. We can see WZ is being set for each instruction. And we get down to the bottom. That looks better. And remember to tick myself off mute this time. So the resulting final failure we had was that the expected addresses written to the log needed to account for that no-op. So the vectors I was using was a no-op followed by a call, so I could replace the no-op for debugging. I'll leave the no-op in. I need to reflect that here. And now we can start removing all of our debug stuff. We know we're getting here. We still have to implement the function. We are going to stop printing that, and we're going to stop printing there, and we're going to stop printing there, and we're going to stop printing there. And this compile takes a while because I am forcing it to regenerate the PNGs. Okay, so now we're running. So that took a lot longer than I had thought because I totally forgot to ditch the 2 immediate execution cycles. And that means that I want to go back to just listing these guys in order for each of the ends to use the opcode macros properly.
Cold, you can just trade with me when we get close
There we go.
to each other.
So that's the RST instructions. And we are how far into the stream? A bit over an hour. Good enough. So now we're going to work on XTHL. I'm just going to do all these in one commit. XTHL is a stack operation. It's a bit complicated because what we want to do is pop HL off the stack and then push the old HL back onto the stack. So we're actually going to pop onto WZ and then push HL, and at the last instant slam WZ back into HL. That's pretty much like what the PDF does. Let's bring the PDF and look at it. So the PDF has an error here in XTHL. You'll notice that if you scan across this line completely, SP is incremented by 1 here, and it is never decremented. It needs to be decremented here. And if we actually wanted to do a push followed by a pop explicitly, we would be mirroring the pop operation, or pop followed by a push. We'd be doing SP minus 1, we'd be doing SP plus 1 in M2. We'd be doing SP plus 1 in M3. We'd be doing an SP minus 1 the cycle before M4, so nothing here. The SP plus 1, SP minus 1, that cancels out. And we have to do an SP minus 1 here so that this gets to the right place. So what's missing in this line is we need decrement SP after it goes out here. So XTHL will have its own custom handlers for this entire sequence. Now, if it can be very like push and pop, but there are those critical differences in how SP is handled and how WZ is used to carry the incoming value that make it a little difficult to merge. And we may merge that back in later. I grabbed the wrong window. There we go. Actually, on my desktop, I grabbed the editor window and moved it off to the side instead of the PDF window. So, remove the PDF window. So, I think what I am going to do is I'm going to go down below all the declarations here and put in the declarations for XTHL. So, static F8080 state I8080 XTHL M1T4, and it does not have a T5. It swings into M2 T1 2 3. This pops the low byte pop byte that will go into L, pop byte that will go into H in M3, push H onto stack, push L onto stack, now, I can't actually avoid committing any changes back to HL because we are just working directly with the IDAL here. Now this goes into, let's get the registers right, this goes into Z. will go into L later. Read byte stack plus 1 into W. That is correct. We'll go into H later. So that's the operations that we need to do.
Sorry, I heard hit the gong. I wasn't ready for the.
So in the real CPU, the latching of WZ into HL is done in T4 and T5 of M5. So let's do that correctly. Okay. So I am going to refer to the PDF while I'm doing this. XTHL, I think I can show this on the screen. Hold on. View. One page. Narrow it down a bit. There we go.
No Gucci purse.
So if I put comments on these declarations, I can copy the declarations down below and start filling them in properly.
We have
So,
a healing headpiece.
XTHL,
Healing headpiece.
if we were to do this explicitly with manipulating the SP like what we've got there, Still do that, and we do.
Let's get some bus out on people, some people that need it.
Okay. Then we start our pops. I am now seriously seeing that I'm irritated by having to write the wait states in. So for long-term maintenance, I'm going to start collapsing all of the similar stuff. I already showed the org file I was producing. See if I can collapse it together in some macros somehow. Okay, so the pop instructions, pop part of it. So XTHL went into Z here, went to W there.
Good drops.
Okay, so the same SP, the SP got incremented, so we're going to do the same thing. So it's S right this time. Oh, wait a minute. Right?
I've never heard of that either.
No, this is an S read. Hold on.
Okay, so it does use the lure. It doesn't give you the lure back. So don't do it again, because I ain't got no more. Well, I had 2 lures on me, but they cost a gold too, so. You can't make these lures. You can only buy them from Nate Hagel. No, so I got some in on an alt in the bank, but I just buy them from Nate Hagel. He's my drug dealer. He lures me in.
Okay, so here's the correction. This guy right here, where we need to, here we incremented IDAL into SP and used it here, and we used it here. We need to decrement it again so we can use it down here.
Anybody interested in? Where's that going? Cold on her. He wants to go pole dancing. He wants to go pole dancing. We have snakes. Do not hug the wall. Don't pull more.
Okay, so with that in mind, one more desk check. So stack pointer is on the address, gets incremented, and we read data into Z. Stack pointer incremented is on address. We're going to leave it pointing at that top guy rather than incrementing it and decrementing again before we use it. We get W. Same address. We're going to write H, and then we're going to decrement
Yeah, they're being kind of chintzy
back to
today on the top
XSP.
eight so far.
Then we are going to take that address and we're going to write L there.
Okay, good to
There
know.
we go. And I'm going to go all the way down to the bottom of the file for this. Defined as a function returning a function, of course, because F8080 state is void. And I'm going to fix this the easy way. We're just going to hand edit this to be correct. T3, T1, T2, T-wait, T3, I would have been justified in, when I noticed that the macro was wrong, in just going back and undoing and redoing a better macro rather than what I did here. Okay, so these are now all defined but not used. So each one of them wants to have a switch and wants to chain into the next one. I'm going to start off by inserting the switch statement first. Make sure this is correct.
We got part of the
And I'm going to
BES ring set. That's good.
go in here and
Grizzly bear in 3, 2, 1. Offset, give me a roll 99.
okay, so now I'm going to work my way up through the file, patching each function name into the preceding null.
This is for hunters and mages. Tokens for hunters and mages.
Let's try this again.
Getting left on the body. And once everybody leaves, I will check the hoodoo file.
And I forgot to put the break in, so we'll just do that now.
Did we have anybody that needed the madness today?
Okay, that should link them all up. This is the only one not used yet.
Just a little room thought in that pile.
So stacking it now needs to come in and say CPU arrow M1 T4 of op XTHL is equal to that guy. So if we were to run this, it would simply take the right number of T states, having done nothing. I think I need to get something more to drink. I'm getting kind of thirsty. I'll be right back. Okay, here we are. And now the other bit. This is such boilerplate here. There's got to be a way I can macro my way out of all of this. So we are going to be doing a decode here. So this is complete. Now this is a pop. So I'm going to go down into deafen. Let's see. I can turn off the PDF now. And I'm going to be using the push and pop control stuff on the right as my template for what I'm doing here. So pop has a machine cycle 2 T1, which will pop into one of them. So I'm just going to grab the working guts of it and copy it in. So read byte at stack into Z will go into L later. So SP into IDAL, IDAL into adder, adder is SRead and raise sync. Okay, M2 T2. We drop sync, tri-state data, raise data bus in, and increment SP. And when we are down here, if val of ready, so if we're ready, we're going to go to T3, otherwise we go to T-wait. Same thing here. I'm going to elide, well, no, let's keep it matching. T-wait, we have to raise the wait signal. Sync data dbn, a set ASP, that's correct. Okay, so T-wait raises the wait signal. We need to re-raise dbn. Okay, and T3, we lower wait. Now the register that we want to set here, scroll back up at the top of M2, this goes into Z.
Here we go.
Okay. Second byte into W. This will differ from the previous in that it does not store the incremented SP back. So I am going to just, actually I'll copy M2s into M3s. Keep my original comment, which I will then have to check. And down at the bottom, we go to M4 T1. So the difference here is we're writing it into the W register, and we are not yeah, let's leave the comment around here.
This is one of the prettiest roads in the game. Going to Logalex in 3, 2, 1. Congrats, Logalex.
Okay, M4.
Nice, deep burgundy.
M4 looks a lot like pushes.
We have a healing mace,
So we're going to go down and look at push M2T1.
ready. Go into Holy Death. Hunter Mage token.
So same dance here as the push. We have already, we had a post increment of the SP followed by a pre-decrement of the SP, which annihilated each other. And let's see, anything else we need to set? No, that's correct. Okay, so phi 2 of the T2 cycle.
Caffeine is way back here in the spider ring.
We are going
I'm
to
on the way.
decrement SP back to its original value. And the value that goes out here is the H register.
Purple diamond. No, Moosh.
And M4T3, phi 1 rise gets the, so we strobe the right signal. Raise right and release the address. Now, while I am thinking of it, I want to go back and check to make sure that when I raised weight during the T weights, I remembered to lower it. Yep, there's the one lower, and M3T3. There, so we did remember to lower the weight. Okay, so SP goes out, IDAL to adder, write the data, decrement SP, lower sync, read the data into, no, send the data to data from H, strobe the right. Okay, M5 T1, D1, T2, T3, I'm just going to copy from M4. So SP goes out again. We decremented it back to the original value, so it's correct now. IDAL goes out, doing it right. We're writing the L register. We strobe it. We head on to M5T1. No, we don't. We head on to M5T4. M5T4 is going to be, first of all, WZ into IDAL. That, and this guy is D set. Yeah, H is IDAL. There we go. A little bit indirect, but I wanted to use the architectural features so that in the future when we look at what's going on inside IDAL, it will have the right stuff. Now let's make sure we didn't trigger that. Okay, we're good. So I believe XTHL is now implemented. So let's go look at our stack test. Basically on stack test, we popped a whole bunch of things into registers, and then we pushed them back into memory. We're running Shadow the way it is. So how can I add an XTHL test to this? So we popped, but it been down to here, and then we pushed back to here. I can put a value. Yes, that's how I'm going to do it. So SP currently points at data, so just below data, I'm going to push DE, I'm going to XTHL. Okay, so that'll push 1, 2, 3, 4 on the stack, and then we'll replace it with 5, 6, 7, 8. Okay, and I'm going to push HL again, and I'm going to test complete. So the 4 bytes before data in RAM are going to be the HL word and then the DE word going backwards. So now if we run this, we should have test failures in the stack test, which we do. 127, 126, 125, and 124. Let's see. So this should be the plot from the XTHL portion of the test. So we're loading DE with 1, 2, 3, 4. We loaded HL with 5, 6, 7, 8. Then we fetched XTHL at address 18, which is here. We have a big long time before next M1. We did 2 mem reads and 2 mem writes, that's correct. 7E, 7F, 7F, 7E. Yeah, okay, that's the correct address because we pushed DE and then we did the XTHL. So 7F, 7E, here's our 2 writes that sent out our data. If we scan up to our data bus, where'd I put that? Data's down here. Hard to see. We do see a 1, 2, 3, 4 snuck in there. And then down here, we are doing our STHL. We're reading FFFF.
Yeah,
Because this is still
yeah,
running.
only the person who won
Right.
will be excused.
So the reason why this didn't work is because when I did the pop here,
So
the
this
reading
time
from
it
the
should be
XTHL
hidden,
came from
shab,
memory.
and inspo rolling.
So let's correct this so it'll run without releasing shadow. So at 7C,
Caster DPS ring, part of a set. Going to Logalex
Okay.
in 3, 2, 1. Congrats, Logalex. Our little shadowy priest.
so 3, 4.
Healing cloak.
So it doesn't really matter what we're pushing on the stack here.
Going to Aya.
I am going to push 1, 2, 3, 4 so it does match what's in the ROM. The XTHL is going to read from the ROM, so it'll read the 3, 4, 1, 2, and now this should be improved.
Staying on the, going to Aya.
And it is not. So what are our addresses that we're dealing with? Well, let's see. If I do a test complete before and after the XTHL, that should get me more details on the plot. Oh, so I'm a complete idiot. Of course we're failing because we didn't change the test conditions. So, yeah, what we should see in 127, well, if we look here, so this is saying we expected 5.5, which was what we wrote there. What we reserved was 5A. So RAM still had 5A in this location. That's not correct. Oh, I'm pulling a test complete here. No wonder. Okay. These need to be next subtests. So this is saying that somebody wrote 34 too far down in memory. Let's regenerate these PNGs. So this guy, plot number 3, should be this much. So LXI, LXI, push. Got that? Plot 4 should be the XTHL itself.
What's your profession?
So here, adder, let's
Yeah.
look at stack test.lst. Here's the XTHL at 1.9. So 1.9
Yeah,
gets the
limited.
E3 instruction.
It's like
3.4,
limited
1.2.
something potion.
So it's a 1, 2, 3, 4
Not
that is
yet.
being brought in from memory. That's correct. And we're writing out 5, 6, 7, 8. That's correct. The addresses that we are reading from and writing to, we're reading from 7E, 7F, then 7F, 7E. Okay, so we should see 7, 8, 5, 6. And then this is our final thing where we push the values from HL. So what HL got, we're going to write back out to memory so we can see that we got something. And here's the 1, 2, 3, 4 going out to memory at 7C and 7B. Off by 1. So we're decrementing the stack pointer one more time than we should. And in fact, if we look at SP, DCB. Let's unify those two plots.
We have the other half of the caster DPS ring set. Going to Logolex, congrats.
Okay, so
This focus can be for
XTHL
casters or
and push.
casters or healers.
Data go out to memories
think it's
5,
underrated
6,
in
7,
the,
8, 1, 2, 3, 4,
Whoever does those data
7F,
mining systems.
7E. So we're getting decremented an extra
Okay, the
time.
float's going to DE.
E, 7F, 7F, 7E. We should remain at
Flock, can
7E.
you give that to Aya? Aya, didn't you get the healing float?
D, C, B. Okay, let's take a look at the code. I give up.
Because the healing float's better than that. That one's good for casters or healers if you've got the healing float, Aya. And this is for priests, warlocks, and druids.
So we
Yeah.
should be incrementing it here in
That's fine,
M2T2
you know.
and decrementing it here in
Nobody for this.
M4T2.
Staying on the body.
I bet you we're decrementing again in M5T2. Yes, we are. There we go. All done. So now we have this, and I can check it by eye as I am picking up the test results. So this should be the low byte of what we had in HL after the exchange, which should be 3.4. And we go back over here and we see that indeed we are seeing 3.4. 3.4, 1, 2, 7, 8, and 5, 6. Boom. Score. So, combination there of bugs in the test where I wasn't checking the proper result, combined with bugs in the source code where I was decrementing SP in extra time, all fixed. There's XTHL. And at this point, you'll notice we have 0 unimplemented instruction codes. So in theory, we now have a functional 8080 CPU chip. We don't have the rest of the system for it yet, but this should be a functional 8080. There's our net change. Let's bring up the Get Kraken and take a look at this. And I've been on mute. So we have now pushed our RST and XTHL to GitHub. I still have some comments to write, and when we come back, we will swing into simulating some devices. We are at a minimum going to need console in and output. So it's some way of me typing characters on the keyboard going into the simulation and text coming from the simulation coming back out into a terminal window, and I have a way of doing that. I used to do a whole lot of network programming, and that is way back in the bad old days when Berkeley sockets were young and new and fresh, and everybody thought they were a good idea. They're still a good idea. It's just that not everybody is on board with them. So I have demonstration code based on code written in the mumbles. I think some of that code actually it dates all the way back to 1985 when I was working at Color. We did I got into networking back then because we were doing some distributed computing where working with other vendors of other mini supercomputers, you would dispatch jobs over the network to the destination computer. The idea would be that your computer running the problem didn't care if the guy on the other end was a Color 7 or one of our competitors. It was all put together by Sun Microsystems. It was called a Connectathon. And they were mainly thinking about file systems, but we also brought in RPC and did these demonstrations. And I worked on that to get our machine basically doing the demonstration problem, which was solving a portion of a Mandelbrot. And I believe some of my socket code dates from back then. Anyway, so what we'll end up with is a bidirectional network socket where we have a server, which will be essentially a terminal multiplexer. So there's a place I can type. and that's a server. So the simulator will call into that, will call that up as a service, and it will say, please send me data, here's some data to print. So the server end of it that I'm typing to is sitting over in the X terminal somewhere else.
And warrior, mage, warlock.
We'll need that. We'll need something similar to that for paper, tape, punch, and reader, which will redirect to and from a file. There's a listing device, which I want to support, a way of producing something that would go to a line printer. Mass storage. I need to have a simulation of a floppy disk drive of some sort. At least some way of saying, please fetch this track, given a track number and a sector number, I want to be able to read and write that data. That's all coming. I think we are done with Kraken. So that's all fine and dandy. Once we have all that, we can start thinking about writing a real honest bootloader.
It's all right. I'm across the river.
LST, we've got some of that going here. We don't really have a bootloader. I've got the copies of, for instance, the cold start from the MDS-80. I've got their loader code, which is basically a relocation thing. The destination of what I'm looking at is we have this CBIOS, which is the bit of CPM that interfaces between the portable CPM operating system code and the actual hardware. So this is the skeletal CBIOS. All of these functions here get filled in. Well, the top bit of it is pretty standard. This is booting. It assumes some things about the layout of the floppy disk. It doesn't really assume them. It's documented requirements for the first two tracks of the floppy disk for CPM bootable floppies. Below that are the bits of code that we will need for everything else we do. Things like consoles. Do I have a character from console? You can get a character, put a character, list, punch, reader, and so on. The disk interface is really relatively simple. There's function calls that keep an idea of what your current track and sector and disk number are and where you want a DMA to and from. And then there's read and write, which we have to write. These are all hardware specific. So part of porting CPM to a new computer is constructing these routines, which would pick up all the data we've done above, package them together for whatever your disk controller is, and do the right thing. Now, this particular bit of text here, I need to go back and look at the format of the data moving to and from the floppy disk drive, because on the floppy drive, on the floppy disk itself, each track is essentially, it's just magnetic tape. I mean, it's a tape stood on edge and spiraled around. So you read a track, and you're going to get a whole bunch of bytes of data, actually a whole bunch of bits of data. And as the floppy disk controller is seeing this digital signal come in from the head of the disk drive, it's going up and down, up and down, up and down. It needs to find out, first of all, it needs to synchronize. So if it just started gathering bits anywhere, it would just be garbage. So it has to know at some point, this is the first bit of a byte. It has to be able to say, okay, I'm starting to read data here. It has to know which sector it's reading, because you literally, on some drives, you may be reading and writing entire tracks, not likely, but you might, or you might be dropping the head and waiting until you get to the right place to write sector number 20, and then you write sector number 20. So there's going to be a gap between sectors. There's going to be something you synchronize on and a sector number, and then you have the data for that sector. And apparently there is deleted data versus non-deleted data for sectors. So I will have to look into that and see if I want to model it. Some systems, you drop the head and you read the track, And as the track comes in, you shuffle it into the right place, so you end up with a image in memory, which is just the data from that track in the proper order, laid out, so that it's in order, just the data, and you modify it, and then you write the track back. One of the best systems I worked with actually had 3 track buffers internally, and when you first read something, if it didn't have the track, it would seek the head out to that track, drop the head on the disk, and read all, the next sector it came to, it would start reading it into memory. It would read all the sectors into memory and have a fully buffered copy of that track. And now you could read and write any of the sectors on that track just by operating in memory, not even going out to the disk. And when you're all done, it keeps track of which tracks have been modified. You've got 3 of those tracks, so potentially you have 2 tracks being read and 1 being written in a lot of apps. Later on, you might end up with 3 dirty tracks in memory, and you need to read a 4th track. You take the oldest one and you seek to that track number, and you write that track back out. And it's essentially a cache. Worked very, very well. This is the Stratos Z80 that did this. It actually had extra memory banks that it would switch in to do these operations. Very clever stuff. Anyway, apparently there was some way of marking sectors as deleted data. That would certainly help in recovering a file system if something went wrong. Anyway, so that's where we're going next, and I think now we're going to call it a stream. So let me head back to my thingy here. There we go. I have no comments I need to respond to. So I'll see you in the next one. Until then, keep it small.